Hello, my name is Camden Clausen, and along with my team, we will be presenting our project titled Steganography, a Forensic Framework for Enterprise Security. Steganography is the practice of hiding data inside normal-looking files like images, documents, or audio. Because these files appear legitimate, they can easily bypass traditional security tools. Our project focuses on a key problem, and that is how enterprise forensic workflows are not designed to detect this kind of hidden data. So today we'll walk through why this is a problem, what existing research tells us, and most importantly, the workflow we developed to help organizations detect steganography more effectively. To structure our project, we broke it down into three main layers: problem, analysis, and solution. First, we define the problem by explaining why steg-exposed detection is weak in enterprise environments. Next, we look at the literature. This includes traditional statistical methods, tool-based approaches like steg-expose and OpenStego, and more advanced deep learning techniques. From there, we identify a major knowledge gap, which is detection methods exist, there's just little guidance on how to integrate them into real-world incident response workflows. Finally, our contribution is a proposed workflow that fits directly into the forensic and incident response lifecycle. The core problem is that enterprises cannot effectively detect steganography, especially on a large scale. First, organizations deal with massive volumes of data, making it difficult to inspect every file for hidden content. Second, most incident response workflows do not include a clear decision-making process for steganography. There is no standardized triage path that tells analysts what to check and when to check it. Because of this, analysts are often forced to choose between fast but shallow detection methods or slower, more accurate techniques. This leads to inconsistent results, missed hidden data, and delays in investigations. This is important because steganography can be used to hide sensitive data, command and control instructions, or even malware. Manual review alone is not scalable, and without a structured workflow, organizations are likely to miss these threats entirely. This gap is what our project aims to address.
As stated in class, steganography is the art and science of concealing the existence of information transfer and storage. A covert sender embeds information and a covert receiver extracts the information. During our literature review, we found many domains within steganography that include text, network, digital media, and file system steganography. The continuous growth of technology can make it easier to deploy steganography to embed data. Early stages of steg analysis included the statistical feature-based detection methods, later the subtractive pixel adjacency matrix. This showed that small modifications of a pixel could be detected through statistical modeling within an image file. To address limitations of earlier methods, research shifted to machine learning and deep learning methods. During our literature and tool review, we investigated steg-expose, an open source tool that is designed to detect embedded data in a file by using the least significant bit. steg-expose utilizes multiple statistical tests: sample pairs, RS analysis, chi-square attack, and primary sets. We also reviewed OpenStego, which uses LSB to embed data. Finally, we reviewed NIST 800-86 to help create our proposed workflow.
All right, so once we had our literature review mapped out, we needed a way to actually compare these methods. Not just list them, but evaluate them against criteria that matter in a real enterprise environment. So we built out four-dimension analysis framework: detection rate, false positive rate, deployment cost, and scalability. Because at the end of the day, a tool that's 99% accurate but crashes under high volume is still a liability, a huge problem. What we found was pretty telling. Traditional tools, your LSB checks, your statistical analysis methods actually scored well on a detection rate. So they're reliable for what they're built for. But the moment you try to scale them across a large evidence set, they start to break down. That makes them a huge liability and a big problem. They weren't designed for that kind of throughput. So deep learning approaches, on the other hand, flipped that equation. Better accuracy, more adaptable, but they come with real deployment complexity. You need to take your time. You need the infrastructure, the compute, the setup. Not every SOC team has that on a day one. So neither camp wins outright. That's actually the takeaway from this section. The gap isn't just about which tool is best. It's about the fact that no single tool covers all scenarios. And right now, enterprises are just, well, they're picking one and hoping for the best. So what we need to do is prepare for the worst while hoping for the best. Which sets up exactly what we're going to propose next.
So currently, right now, there is a knowledge gap within the industry. There's no current incident response frameworks the analysts can use to guide them through stenography detection. And so that would generally mean that the analysts are making more decision calls and more like judgment decisions, essentially. And without having that guidance to refer to a specific framework in terms of how to analyze the data that they're seeing, this really increases the chance of the analyst missing any sorts of evidence, and this can cause a lot of problems. And so, because of that, on the next slide, there's a proposed forensic workflow. And so, basically, in this specific workflow, it integrates stenography detection as well as including that with standard forensic um, incident incident response lifecycle. So it would be triggered by certain types of files, anomalies, or threat actors. And so by treating, so basically by having this type of defined steganography detection, it would allow the investigators to basically apply the right tool at the right stage and not making those judgment calls. And they would have a consistent source of framework that would be creating um, effective and productive timely responses instead of slowing down the process. And so to look at the framework below that we have, the first step would be data collection. So it would be collecting data from network traffic, endpoints, and emails. And basically from that point on, the analyst will monitor for the packets for any anomalies. And the next stage would be the examination. So basically it would and look at the data that they see and classify it, and they would classify it by looking at any irregularities within within the data. So it could be size anomalies, metadata, and any sorts of inconsistencies. And the third workflow would be the analysis phase. So and the fourth phase would be extraction and validation. So basically, it's trying to um, attempt to basically extract any suspicious or hidden files within that specific data that's probably hidden content. And from there, they would probably want to work on analyzing the nature of the data. So just wanting to understand what type of sensitive information is there, if there's any type of sorts of malware or decrypt any coded messages. And from the next and final step, it would be reporting. So basically, providing the documentation of findings and the steps and methods that were used to complete the analysis process and the extractions, and how they collected the data in the examination phase, and and then from there map it to an incident response process, and from there see if there's any security adjustments that may be needed to make as an organization or maybe within the examination process. And so that's what this forensic workflow provides.